Okay, so I can give you just one piece of information about the test. I just got the scanned results back. The raw average, the average without any adjustment was 62%. Okay? That was a hard test. I'm pretty pleased with that. It's a hard test. Many of you did well. Okay? So there were many of you who got 80% and up, which is good on this exam. Okay? Just watch Blackboard. As soon as I crunch the numbers, get your scores into Blackboard, and you'll see your results maybe tonight or definitely tomorrow. Okay? Just watch Blackboard, watch announcements. Okay, so today is a very cool day because we're going to take all this, everything we've worked on really hard so far, and we're going to start our journey in calculus. Okay? And so the first thing we need to do is, are there any other announcements? Morgan, Julia, anything else? Any other announcements or you can think of? Just let me know. If you think of anything, let me know. Okay, so the first thing we're going to do is we're going to kind of refine our meaning from dx. So we really worked hard on this, what this thing is, dx, and as what did it mean? A change in x, right? And that change, it's different than just x because it can be, that change can occur at any value of x, right? It can start that we could think about a change starting, and we were going to call the amount of change dx, but it could start at any value of x. If dx is 2, right? It would be a change. It could be starting at x equals 1, or it could be starting at x equals 10, or x equals -3. So we really worked hard on that, and so that was our meaning for that. And to calculate it, if you had a final value of x and an initial value of x, you would just subtract. It will give you that change, okay? So up till now, we've simply said a change in x, right? Change in x. But now we're going to kind of qualify that. It's still a change in x, but we're going to say that it's a really small change in x. So we're going to do all the same stuff we've been doing, but now we're going to say that dx is a really small change in x. But everything else still applies. Everything else still applies as we're working with like the relationship of dy and dx. That's still all good. It's just that dx is going to be small now. So we were letting it be any size change. Now we're going to let it be small. Okay, and then so it's called the differential. All right, so that little change in x dx is the differential. Again, it can occur anywhere. It can occur at any value of x, and then it means a little change in x. And so now we're starting to talk about calculus. When you're examining what's happening with changes on a very small scale. Now we're really talking about calculus. We're getting into calculus, I should say. Okay, so the differential, a small change in x. Okay? So now if we have related variables x and y, talking about the differentials dx and dy necessarily implies constant rate of change. Now, anytime we're talking about dx and dy, that means we're talking about constant rate of change. And that should be okay because that's all we've talked about so far. But just know that those symbols, dx and dy, they imply that you're talking about constant rate of change. And which means that dy must be a constant multiple of dx, right? That's what we said. dy equals m dx. Given any change in x, dy is that constant multiple times dx. So nothing new there. Okay, so let's talk about speed. And when you talk about speed, there's a man who this applies to, right? Who is this? Usain Bolt. Runs at insane speeds, right? So he broke the all-time world record in the 100-meter sprint by finishing in 9.58 seconds. Let's see that. That'd be fun.
Paul ist der schnellste aus den Blöcken. Jetzt kommt er
photographers are trying to keep up with him. Okay, so what did he do? He ran 100 meters in 9.58 seconds. No one has ever done that before and ever since. And this was, I think, what was this? 2009. 2009, 8 years ago. Okay. So we want to talk about, and we know speed has to do with rate of change, right? It's the rate of change of distance with respect to time. Rate of change of distance with respect to time. So how fast did he run in miles per hour? How fast did he run in miles per hour? So that would be a question much like the one we did right in the first day, first couple days of class, first week. So why don't you just talk through every set of parentheses with the person next to you. What's every set of parentheses mean in this, and how that gets that he ran 23.3 miles an hour. I can't even bike that fast. Okay. All right. So just take a minute. Go and figure out every set of parentheses. What's the meaning of every value in the set of parentheses that gets us this value, 23.3 miles per hour? Go. Okay, so I'm confident that you were able to talk through that. So 23.3 miles per hour. Did he run at 23.3 miles per hour for the entire race? No. Well, that's what we get when you take 100 meters in 9.58 seconds, right? So then what is that number? What is the 23.3 miles per hour? If you didn't run at constant speed for the entire race, what's the 23.3? Okay, what's that? The average, what's that? Do we add up a bunch of speeds and divide by the number of speeds?
Something like
Not really, right? I mean, so how many speeds did he run in the race? How many different speeds did he run in the race?
an infinite number.
He wants an infinite number. Did he run an infinite number of speeds?
Yeah.
All right. Well, so when you have 23.3 miles per hour, or whatever that meters per second was, that's just one number. So that just represents a constant speed, right? That just represents a constant speed. But he didn't run at a constant speed, right? His speed changed. You can't start from rest, not moving, and then get to a faster speed without speeding up. You have to accelerate. You have to speed up. You can't just go from being at rest to being at a speed. You have to travel. You have to speed up gradually. Okay? But this 23.3 miles per hour, that's just one speed. So that's like a constant speed. Okay, so what is that? That's like if someone else ran the race, right? Someone else ran the race at a constant speed of 23.3 miles per hour, what would happen? They would tie, right? They would tie. So that 23.3 miles per hour is like a someone else, a fictitious runner who just maintained a constant speed the whole way, and then they would travel the same distance in the same amount of time. So it's like a phantom Usain Bolt. The speed that person would have to run to achieve the same distance in the same time. Okay? So Actually, so like we said, he ran lots of different speeds. Here, this says that 1 second after the start, he was running at 13.754 miles per hour. At 1 second after the start. What does that mean? What does that mean? That at 1 second after the start, he was running at 13.754 miles per hour. See, that's another single number, so it can only mean like a constant speed. Okay? So here's Usain at exactly 1 second since that's elapsed in the race. How fast is he running at exactly 1 second?
No, he's not running because we've frozen time. He's not moving at all.
Okay. I think he's onto something. Is he moving? No, it's exactly right. If you say at the instant or at exactly 1 second, you freeze time and he's not moving at all. So really, technically at 1 second, at the instant or exactly 1 second, he's going 0 miles per hour. You see that? He's not moving. You're seeing it. You're seeing it right there. He's not moving. So we want to consider this. So here's Usain at the moment when 1 second has elapsed in the race. How fast is he running in this moment of time? Let me zoom in now on that picture. If I were to zoom in on that picture, what do you see? He's blurry, right? He's blurry. So to talk about his speed at a particular time, we can't talk about it exactly at that time. We talk about what's called a moment of time. And a moment of time implies what? What are we talking about then? A moment of time. A really small change in time. For instance, so like the time that the shutter was open and there was a blur. You did some homework with the car, right? So that the idea of the blurry car is that the shutter is open for a moment in time, not at a particular time, right? So in order to talk about speed, what speed is about rate of change. Things need to change. If things aren't changing, then you can't talk about rate of change. So what we need is a little change in time, which we call a moment. And then we can talk about what it means for the meaning of that speed, 13.754 miles per hour. So how fast is he running at this moment of time? At this moment of time, he's running 13.754. So let's take a look at the graph of his distance from the start versus his time. So here's a graph that simulates, it's a simulation of that race, where the x-axis, or independent variable, is time since the race started, and then the dependent variable is his distance from the start. His distance from the start. And so we were talking about at the moment 1 second. So now I've zoomed in here. Here's 1 second, and what do you notice about this graph? What do you notice about this graph?
It's not linear.
Right, it's not linear, right? So what's actually happening here? He's accelerating. At the beginning of the race, he's speeding up in the first 2, 3, 4 seconds. He's speeding up. So what does it mean that at the moment 1 second, his speed was 13.574, whatever that was. So I'm gonna go right there, and I'm gonna watch this. I'm gonna zoom in on the graph. What happens? If I take a small enough interval, it appears linear. And now, if we have a linear graph, we've got constant rate of change, right? We've got constant rate of change. And now this number, this miles per hour, this 13.574 miles per hour, can make sense to us as changes in distance versus changes in time, according to our constant rate relationship, right? So once I get zoomed far enough in so I have a linear relationship, then everything we've learned so far applies. But if I'm back out here, we can't use dy equals mdx, right? We can't use dy or this because we don't have constant rate of change. As soon as we change our change in x, then we've got a new rate, right? But for a small change in x, all our mathematics about constant rate of change that we worked on now applies. And then if we move to a new time, then it would be the same thing again, but for a different rate. So this is why we work so hard on all that, because even if you have a non-constant rate function, a nice, smooth, continuous, non-constant rate function, constant rate of change still applies if you look at a moment. If you look at a moment around a particular x value, okay? A small enough moment, I should say, a small enough moment. So let's go back, finish this one. So, a moment is a small change in the independent variable. Let's look at that. So a moment, we said it's a small change in the independent variable. So now dx, now we said dx, our differential, we also said was a small change. But they're not the same thing. Okay? And our experience is that this difference doesn't come quickly, so try to really focus in, tune in here. Dx is not equivalent to moment. It's actually usually smaller. All right, it varies within a moment. Okay, so we have a moment that's a small change, and then within that moment we think about dx, and dx itself varying within that moment. So we'll do examples. Okay, then there's another thing that we call rate of change at a moment. A rate of change at a moment exists if there's a small enough interval where the rate of change is essentially constant. That's what I just showed you at t equals 1 second, right? I zoomed in at t equals 1 second on this graph. If I zoomed in far enough, there was a small enough interval where the graph looks linear. So that's what we call a rate of change at a moment. A rate of change at a moment is a constant rate of change that exists if you can make for a small enough moment. Okay, small enough interval where the rate of change is essentially constant. Okay, and so then that constant rate in that moment at 1 second is his speed at 1 second into the race. And we know we could calculate that speed. How could we? So I've zoomed in at 1 second, and I see that it's essentially linear. So remember I had it like this. I zoomed in, and it was essentially linear, say right there around 1 second. So maybe this is, what, 0.995 or something? And 1.005. So how would I calculate his speed? How would I calculate his speed at the moment 1 second? How would I calculate his speed at the moment 1 second? Yeah. Well, the average of those x values would just be 1. So we're not going to average the x values. How would we get his speed? So this is his distance from start, right? And this is time since starting the race. How would we get that? Yeah. Yeah. So now that we have a little part of the curve that's straight, we would need a change in distance, like a dy and a dx, and then that ratio dy over dx would give us that constant rate, which we would call the rate of change at the moment, 1 second. So we would just, if we had two correspondence points in that little interval, in that moment, we could take dy over dx, and that would be the, in this case, meters per second. Meters per second, his speed. Now, move to 1.2 seconds, we could do the same thing, but it'd be a different speed, right? It would be a different speed, because we know he's speeding up now. He's speeding up now. Okay, so we're going to do some practice with this, and we're going to practice all these things we practiced before, which was identifying information with symbols, function notation, constant rate of change. All this stuff is going to apply. So here's the beginning of that distance time curve of him running the race, right? So the x-axis is time elapsed since the start. We're using x here. And then this is the function f, which gives his distance from the start, or distance ran. He's running a straight line, so that's the same thing. Okay, distance from start and time. And so again, we're interested here at what's happening at 1 second. And so you see that little blip right there? Here's what that really is. So here is the same graph, but just from 0.99 to 1.01. So I'm looking at, I took the same piece of that from 0.99 to 1.01, and we have constant rate of change, so we can think about what? We can think about changes in distance and corresponding changes in time, okay? So we're thinking about just a little tiny bit of the race that he ran, right? Little tiny bit of the race that he ran. Okay, so let's look at the situation here. So distance from start, time since the race started, we talked about that. The display graph of f near x equals 1 is essentially linear from 0.99 to 1.01. So therefore, we have a rate of change at this moment. We have a rate of change at this moment. Okay? Imagine x increasing from 1 to 1.006. Simultaneously, his distance from start changes from 3.4882 meters to 3.5251 meters. Okay? And you're watching it happen dynamically over and over again. What's Usain's speed at the moment? X equals 1 second. But remember what we said. What we said about these situations, lots of information, real world situation. We always want to model it. Okay? We always want to model it. So here's what we want to do. For each item, we want to identify the values associated, and then how it's represented symbolically, and then how it's represented on the graph or graphs. Okay? So you want to have a sketch of this, and your sketch can include the quote triangle at its full, at its largest state. Okay, that's the situation we're talking about. And then we want to identify the values that we know of these 6 things, and then how would they be represented symbolically, and then how would they be represented on the graph. So you've discussed it, you've thought it over. So I'll go ahead and put some answer stuff. Okay, so what's the initial value of the independent variable? Initial value is 1 second. 1 second. Okay. Symbolically, x initial or xi. Yeah, xi is fine. X initial I have. X init. Okay. Initial value of the dependent variable. 3.4882 meters from the start at 1 second. Symbolically, I'm not using y. F of 1. F of 1, right? F of 1 gives us the value of the dependent variable at 1 second. So that's what we're using, f of 1. So here's an example of why function notation is better than just saying y. We could say y, even y initial, but this tells us even more, right? Because it tells us that it's the dependent variable of f when x is 1. That's why we like function notation, because it gives us the most information about that y value. Okay, the differential in x. What is the differential in x?
0.006.
0.006. And how do we symbolically represent that?
Dx.
dx. Okay? Or you could have written x final minus x initial, but dx is what? Yeah, dx. Okay? The differential in f. What'd you get for that? 0.0368? Is that right?
Yep.
How do we show that symbolically, the differential in f?
Df.
So we can say df, or you can say Yep, f of 1.006 minus f of 1 is okay, or I just have df, okay? But yes, f of 1.006 minus f of 1 is another way to symbolically represent that. Okay, now for the moment in question, at first we could just say, oh, it's the whole thing we're looking at. That's perfectly legitimate, from 0.99 to 1.01. But there's kind of like, there's not like really one answer to the moment. We could say for the moment, we could say it's from 0.995 to 1.005. Or we could say it's from 1 to 1.001. It's any interval that's small enough so that this thing is linear and our two correspondence points are inside of it. Okay? So the moment it's just a small enough interval so that we've got a linear graph. We've got constant rate of change. So answers can vary on this. So I've written down the whole thing, 0.99 to 1.01. Okay? Or you could say it's from 1 to 1.01. That would be a valid way to state the moment in question. Or you could say from 0.995 to 1.005. Any interval that's small enough so that the rate is constant and our differentials are inside of that. Okay? Does that make sense? So there's no real symbolic notation for that. Okay? The moment, again, it's just any interval that's small enough so that the rate is constant and that the differentials that we're considering are inside of that, are changing with inside that moment. Is it okay? All right. And what's the rate of change? What'd you get for the value of that? I got 6.33.
I got.
Anyway, 6.1 something. Okay, so it depends how we round or how we do the math, but you should have got something close to 6.13 or 5 or something like that. Okay, what? By taking df over dx, right? The change in f over the change in x. Symbolically, what do we do for that? M, right? Or df over dx or m. df over dx or m. Okay, anybody have a question on any of that? So this difference between a moment and dx, we know that this takes a little time for you to get used to. Anybody have a question? Okay, so now we're going to look at another situation at 0.4 seconds, and I'm going to mix things up here. Okay, so now, same function, it relates its distance from the start to the time since the race started. Okay, independent variable. Usain's speed at the moment, x.4 seconds, is 3.05 meters per second, when his distance from the start is 0.702 meters. Okay, so I'm giving you different information. I've changed the order of things, and now I'm asking you to work symbolically first and then the values. So read carefully. And so here's where we're really going to start applying some of the things we've learned before. Okay? Let's talk them through here. See how you did. So for that, so we know that our x value for our first correspondence point is 0.4, and we're going up to 0.408, and actually this animation goes all the way up to 0.415. So our moment has to be, big enough to include those key values of x. So what did I put? I put 0.4 to 0.415. Okay, that was what I wrote. You got to have 0.4's got to be in there, right? So you got to at least start at 0.4. You can't start at 0.405 because 0.4 is one of our key values. Okay, so this is a valid moment, but there would be other possibilities. Okay. All right, the rate of change at this moment, symbolically, dx or m, and what was the value? 3.05, given, right? This time given. All right, key values of the independent variable. So symbolically, x initial and x final, and those values are 0.4 and 0.408. Are we good so far? That's what you wrote? Okay, differential in x. That should be easy, right? We know that's dx, and that value is 0.008. 0.008 for this particular situation. Okay, so that differential in f, there's actually three ways. So the shortest, most compact way would be df. df, not d of f. It's not function notation. It's all one thing, df. Okay? You could also say, to get df, so I have df there. So then I heard some people saying, f of x final minus f of x initial. That would be valid. F of x final minus f of x initial. But the other way that I was thinking of is the key concept that allows us to calculate this value. How else can we express df that is the way that we're going to calculate that value?
MDX.
Good, mdx, right? So we have the rate, we have the constant rate, we have the change in x. So we could write that as mdx, right? mdx. It's probably maybe the biggest theme of the first couple weeks of class, right? We've worked hard on that. And so what'd you get for that? So you're just going to take that rate, 3.05, times the 0.008. I got 0.0244. Is that what you got?
Yep.
Good, okay? So symbolically, how do we represent Usain's initial distance from start? How are we going to show that symbolically? Should have f of 0.4. f of 0.4. And its value? Given, 0.702, right? That's a given value. Okay, final distance from start. Final distance from start. So we just want to represent it in the shortest way possible, but then we want to represent it in terms of the way that we're going to get it, the way we're going to calculate it. So in the shortest, most concise way possible, f of 0.408. And this is like a what? This is like a y final. And how do we learn to calculate y final? Initial plus the change, right? So this is what we also were working hard on. That a final value of our dependent quantity is the initial, which would be f of 0.4, plus the change. So you could say plus df, or you could say plus mdx. And this is final equals initial plus the change. And that's the way we want to, again, so this is all application of what we've already learned, but we're just looking at a really small moment of x. Small enough so that we have the linear constant rate relationship and we can apply all that stuff. What'd you get for that? I got 0.7264. So let me pause it there. About there. So here's the actual frozen. And remember, variables vary, right? So that's why I'm showing this blue line kind of being generated. There was a moment, there was a time where he ran this race, and x was increasing, and his distance from the start was increasing along with that. And all these correspondence points were being generated. You've got to think about variables as varying quantities, right? As varying quantities. So we're just going to frame time here at the moment, or the point where, time where we're at 0.408. And we've got that correspondence point, and what are the coordinates of that correspondence point? 0.408. And what do we say? So we had the initial y value of 0.702. We added the change that we got from mdx to get the final value of 0.7264. And so, please.
For number 5,
Yeah.
why is it d of f and not, or sorry, why is it df and not df of something? F is not a value. Right?
Yeah, so we just use that to represent the dependent variable. So we're just using the dependent variable. So it's a little, yeah, what's that?
So shouldn't it be f of x?
Technically, but that's just like, it's just a little cumbersome. You're right. You're absolutely right. So yeah, if we were being like really super accurate, then he's right. We would do that. It's just, it's not convenience. It's not convenient like df is. But you're absolutely right. The real meaning of it is df of x. Thank you. That's good. Okay, so back to this here. Anyway, so we've got our correspondence point for that point. Okay, so now we want to, or any other questions? So let's represent some things on the graph here. So I've already represented dx and df on the graph. So everything else, let's go ahead and sketch this graph, and let's represent everything else on the graph. So I've shown you dx from 0.4 to 0.408 there, that change of 0.008. Shown you df, which we know is, how much was that change? We got from m dx. But there are other things we can represent on this graph from our modeling up here, what we did. So let's do that. So sketch that graph, and we want to represent everything we did up there on the graph, not just the changes. Go. Did I miss anything? So where do we represent values of the dependent variable? Not at the correspondence points, right? On the y-axis, right? On the y-axis is where we get values of the dependent variable. Correspondence points are two values taken simultaneously, like I've done in blue, there. Just one more thing I want to write is this, just a representation of that last calculation, really important. Okay, that the final value of, sorry, I can't get that thing to go away. So the final value of y, what is the initial y up to here plus the change in y, or f. It's the initial value of f. Sorry, the final value of f, the final value of its distance, is the initial value of its distance, which is to here, plus the change. So this is not 0 here. That's why I'm squiggling, because this is not distance equals 0. So you'd have to go down to wherever the real axis was. Initial to there, the change there, so then that would be that whole the final distance traveled, 0.7264. Okay, any questions on breaking this whole thing down and looking at all the pieces? Okay, so now we're going to do the same thing again. But we're going to repeat this exercise for any x in the moment, 0.4 seconds. So now we're really going to let it move here. So I'm letting that thing move, and so we want to represent all of these correspondence points that you see being generated. See, as this graph emerges, it's emerging point by point. I want to represent every single one of those points in this moment. And so you can work through the same thing again, except you might not always have values over here. You might also have expressions. Expressions of x. So we want to represent every correspondence point in this moment. We're going to repeat it for any x, not just 0.408. Go. Okay, how do we express dx now? How do we express dx? Good. Yep, x minus 0.4. So it's allowing, we get the dx for any x, right? For any x. Okay. df. If this feels familiar, good, because we've done it. So what is our corresponding change in his distance, or what we call df then? We've got constant rate of change. We've got a change in x. Therefore, change in y is mdx, 3.05 times x minus 0.04. How many got that much before I started writing anything? Not enough. Not enough. This is the same thing we've been doing, guys. So if x is any x value, then it's like the x final, but it's allowed to vary, just like it's varying in the animation. So then our dx is going to be x final minus x initial. We have constant rate of change, so changes in y or changes in f are going to be that constant rate times the change in x, 3.05 times x minus 0.04, or 0.4. Okay, his initial distance from start is still, that's f of 0.4, which is, that doesn't change. So here's the key step then. How do we get, for any one of these correspondence points then, how do we write what that distance from start is? It's going to be f of what? X. F of x equals. Yeah. Sorry. Yeah.
Instead of just x just defined, right? X final, or do we have to
Well, so yeah, so I said repeat the exercise for any x, any x. So that any x is, in our situation, is the x final. But we want to write, but so the answer is going to just have x in it. But in this case, it's the same as x final. It's the same as x final. Okay, so then, what is it? The final value of the distance, initial. So we could write f of 0.4 plus the differential, and so our expression is 0.702 plus 3.05 . So for this moment, we can define the function as this, 0.702 plus 3.05 times x minus. And why is that important that we can do that? Because right before this moment was a different moment with a different rate. So having the y-intercept of this is meaningless, right? So right before this moment was a different moment with a different rate. So when we got up to this correspondence point, 0.4, 0.702. Now for this little moment, we can define what the final distance is. Initial distance plus the change in distance, which is calculated by constant rate times the change in time, x minus 0.4. Okay, so this is the third class in a row that we've done that. It's super important. If you didn't get that before I started writing, it's time to get it. It's time to get it. It's the third class in a row that we've worked on that. So study this. This is super important. Okay, check Blackboard for homework. Other announcements. Have a good weekend. See you Tuesday.